On a clear night, far from the glow of any city, you can look up and see a sky filled with what feels like an infinite number of stars. They seem close, somehow. They seem almost reachable, little pinpricks of fire suspended just overhead, like lanterns hung across a ceiling you could touch if only you climbed high enough. That feeling of closeness, that intimate sense of a universe draped across your shoulders like a blanket, is one of the oldest and most profoundly misleading sensations in all of human experience. Because the stars are not close. They are not even close to close. The gap between us and the nearest star beyond our own sun, a distance that has been measured, confirmed, and studied for nearly 2 centuries, is so vast, so incomprehensibly enormous, that every human framework for understanding size collapses under the weight of it. Not bends, not strains, collapses entirely. The star in question is Alpha Centauri, or rather, the system we call Alpha Centauri, which contains within it a small, dim red dwarf called Proxima Centauri, the single closest stellar neighbor our Sun has. And the distance to Proxima Centauri, the nearest star to Earth after our own, is approximately 4.24 light-years. A number that sounds almost manageable, a number that sounds like something you could write on a napkin and hand to an engineer. A number that, when you begin to truly unpack it, when you truly sit with what it means in physical, concrete, human terms, reveals itself to be something closer to a declaration of cosmic war against human ambition. This is a story about that distance, not just the number, not just the light years, but what that distance actually means for physics, for space travel, for the dream of reaching another star, for the future of our species, and for the quiet, almost unbearable truth about where we sit in this galaxy. If you enjoy deep space explorations like this, consider subscribing. Let's begin where most conversations about interstellar distance should begin, but rarely do, with an honest reckoning of how far away Alpha Centauri actually is, expressed not in light years, which are a unit of convenience rather than comprehension, but in something that the human mind can at least attempt to wrestle with. A light year is the distance that light travels in 1 year. Light, moving at approximately 299,792 kilometers per second, the fastest anything in the known universe can travel, covers roughly 9.46 trillion kilometers in the span of a single year. Write that out in full, and it looks like this: 9,460 billion kilometers, 9,460 billion kilometers in 1 year, traveling at the speed of light. Proxima Centauri sits at a distance of 4.24 light-years from Earth. That means the distance between our solar system and our nearest stellar neighbor is roughly 40.14 trillion kilometers. 40 trillion kilometers. If you printed out that number in standard font on a standard piece of paper, the zeros alone would require a line of text stretching across several pages. But numbers on their own are dumb. They don't carry weight, they don't carry feeling. To really understand the distance to Alpha Centauri, you need a comparison, something familiar enough to serve as a mental anchor. And the most honest comparison begins right here, in our own solar system. The distance from the Earth to the Moon is roughly 300 to 84,000 kilometers. The Apollo missions, which remain to this day the only crewed voyages beyond low Earth orbit, took about 3 days to cover that distance, 3 days to reach the Moon. That journey felt enormous in 1969. It was celebrated as the greatest achievement in human history, and in many ways it still deserves that title. But the Moon is, in the grand scheme of cosmic distances, essentially in our backyard. It is the distance from your front door to your mailbox. The distance from the Earth to the Sun is roughly 150 million kilometers. We call this one astronomical unit, or 1 astronomical unit. Light covers this distance in about 8 minutes and 20 seconds, which is why we say the Sun is about 8 light minutes away. The fastest spacecraft ever launched, NASA's Parker Solar Probe, approaches the Sun at speeds exceeding 690,000 kilometers per hour during its closest passes. At that speed, faster than any human-made object in history, it would take this spacecraft roughly 9 days to travel from Earth to the Sun. Now scale that outward. The outer edge of our solar system, defined by the heliopause, the boundary where the sun's solar wind gives way to interstellar space, sits at roughly 120 astronomical units from the sun. The Voyager 1 spacecraft, launched in 1977, reached this boundary in 2012 after 35 years of travel, 35 years of continuous flight, and Voyager 1 had barely stepped outside the front gate. Proxima Centauri is approximately 268,770 astronomical units from the sun, not 120 astronomical units, not 1,000 astronomical units, 268,000 astronomical units. If Voyager 1 were aimed directly at Proxima Centauri, which it isn't, but if it were, it would take approximately 73,000 years to arrive, traveling at its current speed of about 17 kilometers per second. 73,000 years. That is longer than modern Homo sapiens have been behaviorally complex. It is longer than the entirety of recorded human civilization multiplied by a factor of more than 10. It is longer than the time since the last ice age ended, longer than the existence of writing, agriculture, mathematics, music, philosophy, and every form of art and science that our species has ever produced, combined, several times over. This is what Alpha Centauri means when translated out of the clean abstraction of light years and into the physical reality of spacecraft, velocity, and time. It means that with our best current technology that took decades and hundreds of millions of dollars and some of the most brilliant minds in human history to produce, we could not reach our nearest stellar neighbor within a span of time that resembles anything a human civilization could maintain continuity across. And yet, we keep looking at that star. We keep measuring it, studying it, dreaming about it. Why? Because it is the closest one. Because if there is any star in the galaxy that humanity might one day reach, Proxima Centauri is it, and even that closest, most achievable destination is separated from us by a chasm so deep, so wide, so physically brutal in its dimensions, that the word distance feels almost like an insult for describing it. It isn't a distance so much as a condition, a fact about the universe that puts hard limits on what life on this small blue world can ever hope to accomplish. To understand why that distance is so terrifying, you first need to understand where it comes from. Why are the stars so far apart? This isn't an accident or a curiosity. It is a structural feature of the galaxy, built into the physics of how stars form and how they interact over billions of years of gravitational dynamics. Stars form from clouds of gas and dust called nebulae. These clouds, when they reach sufficient density through the gravitational influence of a passing shockwave from a supernova or the tidal forces of galactic rotation, begin to collapse inward. As they collapse, they fragment. Different regions of the cloud reach different densities and ignite as separate stars. This fragmentation process is constrained by physics, by the competing forces of gravity and thermal pressure and magnetic fields. And one of its consequences is that the fragments tend to be separated from one another by distances measured in light years. In the densely packed core of a globular cluster, stars can be separated by as little as a fraction of a light year. But in the spiral arms of the Milky Way, where our solar system lives, the average distance between stars is closer to 4 to 5 light years. Proxima Centauri at 4.24 light years is, in other words, almost exactly at the galactic average for stellar separations in our neighborhood. It is not unusually far away. It is typical. It is normal. The terrifying distance to Alpha Centauri is not an outlier. It is the rule. This fact alone should give us pause. We don't live in a universe that placed the stars conveniently close together, waiting for life to visit them. We live in a universe where the stars are separated by distances that make any form of interstellar travel by any creature, made of any material, powered by any energy source, extraordinarily difficult to achieve within timescales that biological beings would find meaningful. There is a philosophical tradition in discussions of the Fermi paradox, the observation that the universe seems to be full of potentially habitable worlds, but shows no obvious signs of other civilizations. That proposes the distances between stars as a kind of natural filter, a barrier that most civilizations, however advanced, simply never overcome. Not because they lack the desire or the intelligence, but because the physics of the problem are so brutally demanding that the resources and time required to build a true interstellar vessel may simply exceed what any civilization can sustain before it is disrupted by war, climate change, asteroid impact, political fragmentation, or any one of 1,000 other hazards. The distance to Alpha Centauri is, in this sense, not just a number. It is a test that no civilization has demonstrably passed, and that our own species is only just beginning to understand well enough to contemplate the full magnitude of what passing it would require. Let's talk about the physics of that problem, because it is in the physics that the full terror of the distance reveals itself. The fundamental challenge of interstellar travel is not energy production, though that is enormous. It is not engineering or materials science, though those challenges are staggering. The fundamental challenge is the relationship between speed, mass, and the incredible amount of energy it takes to accelerate a spacecraft to the velocities needed to make an interstellar journey in any reasonable amount of time. The Tsiolkovsky rocket equation, published by the Russian mathematician Konstantin Tsiolkovsky in 1903, describes the relationship between a rocket's change in velocity, its exhaust velocity, and the ratio of its initial mass to its final mass. The equation looks simple enough, but its implications are devastating. To achieve high speeds, a rocket must expend propellant, and the faster you want to go, the more propellant you need. But propellant has mass, and that mass must itself be accelerated, which requires more propellant, which adds more mass, which requires even more propellant. The result is an exponential relationship between the desired final velocity and the required initial mass of propellant. To send a spacecraft on a journey to Proxima Centauri in, say, 1,000 years, still longer than recorded history, but the kind of timescale a civilization might maintain records across, you would need to reach a minimum average speed of about 0.45% of the speed of light. That is 0.0045 times c, where CE is the speed of light. That translates to roughly 1,350 kilometers per second. The fastest chemical rockets ever built achieve exhaust velocities of about 4.5 kilometers per second. Using the Tsiolkovsky equation, to accelerate a 1 kilogram payload to 1,350 kilometers per second using a chemical rocket, you would need a mass of propellant so preposterously enormous, so many orders of magnitude larger than the mass of the spacecraft, that the calculation enters the realm of the absurd. The number you arrive at involves more mass than exists in the observable universe. Many times over, chemical rockets simply cannot get us to Alpha Centauri in any time frame that could be called civilizationally coherent. Nuclear propulsion changes the equation somewhat. Ion drives, nuclear pulse propulsion, and theoretical designs like Project Orion, which proposed using a series of nuclear explosions to push a massive spacecraft, can achieve exhaust velocities vastly greater than chemical rockets. The Orion concept, I seriously studied in the late 1950s and early 1960s by scientists including Freeman Dyson, might in principle be capable of reaching exhaust velocities on the order of tens of thousands of kilometers per second, which would make an interstellar journey feasible, in theory, within perhaps a few hundred years. But, in theory, is carrying a lot of weight in that sentence. The Project Orion design would require the detonation of hundreds of thousands of nuclear warheads to accelerate a spacecraft to interstellar velocities. The engineering challenges are so severe, the political obstacles so significant, and the cost so incomprehensibly high that no serious proposal has ever come close to moving forward. Nuclear pulse propulsion remains a theoretical exercise, not a roadmap. The most scientifically credible proposal for a fast journey to Alpha Centauri in the current era is the Breakthrough Starshot initiative, announced in 2016 by physicist Stephen Hawking, entrepreneur Yuri Milner, and a team of researchers. The proposal is audacious in its ambition and brutally honest in its constraints. Rather than trying to accelerate a large, crude spacecraft, Breakthrough Starshot proposes sending a fleet of tiny gram-scale Starship probes, essentially miniaturized electronics attached to reflective sails, and accelerating them using a massive ground-based laser array. The idea is to use photon pressure from an enormous laser beam, a system requiring gigawatts of power focused with extraordinary precision, to push these small sails to speeds of approximately 20% of the speed of light. At that velocity, a starship could reach Proxima Centauri in about 20 years. 20 years, not 73,000 years, not 1,000 years, 20 years, a time frame within a single human lifetime. The proposal sounds almost impossibly optimistic compared to everything else on the table, and yet the physics are real. Photon pressure is real. Laser propulsion is real. The challenges are not fundamental physics violations. They are engineering challenges, though engineering challenges of a magnitude that has no precedent. The ground-based laser array envisioned by Breakthrough Starshot would need to output roughly 100 gigawatts of power, focused on a sail perhaps a few meters in diameter from a distance of thousands of kilometers above Earth, maintained for several minutes during the acceleration phase. The sails would need to be extraordinarily reflective. Absorbing even a tiny fraction of that laser energy would vaporize the spacecraft instantly. The electronics would need to survive decades of exposure to the interstellar medium, including dust particles that at 20% of the speed of light carry the impact energy of small explosives. And then there is the communication problem. A starship arriving at Proxima Centauri after 20 years of travel would need to transmit its findings back to Earth using a laser transmitter the size of a postage stamp across a distance of 4.24 light-years. The round-trip communication time alone would be 8.48 years. Any data the probe collected would take more than 4 years to reach us at the speed of light. The spacecraft cannot be remotely controlled in any meaningful sense. It would need to be fully autonomous, making its own decisions during the brief flyby of the Proxima Centauri system, since no signal from Earth could reach it in time to be useful. These are not trivial problems. Breakthrough Starshot's project team has been candid about the fact that the full realization of the concept is likely decades away, even under optimistic scenarios, and the version that would actually reach Proxima Centauri in 20 years involves a probe that weighs a few grams, travels at a fifth of the speed of light, and spends perhaps a few hours in the vicinity of the target system before continuing onward at relativistic velocity forever. There would be no deceleration, no orbiting, no landing. The probe would blow through the Proxima Centauri system like a bullet, snap a few photographs, and vanish into deep space. That is the best realistic option on the table right now for reaching our nearest stellar neighbor in a human lifetime, a gram-scale probe that can't slow down. That trajectory should tell you everything you need to know about where we stand in relation to the stars. Now let's talk about what Alpha Centauri actually is, because the system deserves more than just being the target of our frustration. It is, by the standards of stellar astronomy, a deeply interesting place. The Alpha Centauri system is actually a triple star system. Two of its components, Alpha Centauri A and Alpha Centauri B, form a binary pair, orbiting their common center of mass with a period of about 79.9 Earth years. Yet Alpha Centauri A is a G-type main sequence star, very similar to our own Sun in size, mass, and luminosity, perhaps slightly older and slightly more massive. Alpha Centauri B is a K-type main sequence star, somewhat smaller, cooler, and dimmer than the Sun, but still a substantial stellar body. These two stars are separated from each other by an average distance of about 23 astronomical units, roughly the distance between our Sun and Uranus, though their elliptical orbit brings them as close as 11 astronomical units and as far as 36 astronomical units at different points in their 80-year orbital cycle. The third member of the system, Proxima Centauri, is a far smaller and dimmer M-type red dwarf, separated from the AB pair by approximately 0.24 light-years, roughly 12,900 astronomical units. Whether Proxima is gravitationally bound to the AB pair or merely passing through the neighborhood is a question that has been debated, though current consensus holds that it is a true member of the system, moving in a very long, slow orbit around the other two. From our vantage point on Earth, Alpha Centauri A and B appear as a single point of light, the third brightest star in the night sky, prominent in the southern constellation of Centaurus. To the naked eye, they are indistinguishable from each other. Proxima Centauri, being a dim red dwarf, is not visible to the naked eye at all. Despite being the closest of the three, the fact that Alpha Centauri A is so similar to our Sun has made the system a favorite target for discussions about the possibility of habitable planets. If planets can form around Sun-like stars, and they clearly can, since we have one, might they also have formed around Alpha Centauri A or B? And if they formed in the right orbital range, might any of them harbor liquid water? And if they harbor liquid water, might they harbor life? These questions took on electrifying new significance in 2016, when a team of astronomers using the European Southern Observatory announced the detection of a planet orbiting Proxima Centauri in what appeared to be the habitable zone. The planet, designated Proxima Centauri B, was detected via the radial velocity method, a technique that measures the tiny Doppler shifts in a star's light caused by the gravitational tug of an orbiting planet. The planet was found to have a minimum mass of approximately 1.17 times that of Earth, and it orbits Proxima Centauri at a distance of about 0.0485 astronomical units, completing an orbit every 11.2 Earth days. The announcement was extraordinary. The nearest star to Earth might have a roughly Earth-sized planet in its habitable zone. For people who had spent their lives dreaming about interstellar exploration, the discovery felt like the universe setting a signpost. Here, it said, here is where you should go, a destination not just in terms of proximity, but in terms of the potential for something extraordinary waiting at the end of the journey. But the subsequent years have complicated that initial excitement in important ways, and understanding those complications reveals something crucial about the nature of planets around red dwarf stars, and about what the universe is actually like compared to how we sometimes want it to be. Proxima Centauri, like most red dwarf stars, is a flare star. This means it periodically undergoes violent increases in luminosity caused by magnetic reconnection events on its surface, the stellar equivalent of enormous solar flares, but proportionally far more intense relative to the star's total output. These flares blast the surrounding space with ultraviolet radiation and X-rays at levels that would be catastrophic for any surface-based biology similar to Earth life. In March 2017, astronomers documented a flare from Proxima Centauri that increased the star's brightness by a factor of 68 over a period of a few seconds, releasing a burst of radiation that would have bathed any nearby planet's surface in lethal doses of ultraviolet light. This doesn't mean life around Proxima Centauri is impossible. Subsurface life and ocean life shielded by depth, or life that has evolved extraordinary radiation resistance, are all theoretical possibilities. But the image of Proxima b as a lush, Earth-like world sitting comfortably in the warmth of a friendly star has been substantially tempered by what we now understand about its parent star's behavior. There is also the problem of tidal locking. Proxima Centauri Ba, it orbits so close to its star that it is almost certainly tidally locked, meaning one side of the planet perpetually faces the star, bathed in perpetual light and heat, while the other hemisphere is locked in permanent frozen darkness. The boundary between these two zones, the terminator line, might be the only region where conditions are even potentially temperate. Whether any atmosphere could survive the combination of stellar flares and intense radiation long enough to create a stable climate is deeply uncertain. In 2022, data from the James Webb Space Telescope and other instruments began to place tighter constraints on what Proxima b's atmosphere, if any, might look like. As of the current state of knowledge, no confirmed atmospheric detection has been made. The planet remains a tantalizing candidate and an object of intense scientific interest, but the confident extrapolation from habitable zone planet to Earth-like world has been substantially walked back from the early excitement. Meanwhile, the Alpha Centauri AB pair has proven more elusive in terms of planetary companions. In 2012, a team claimed to detect a planet orbiting Alpha Centauri b, but subsequent analysis showed that the apparent signal was a statistical artifact rather than a genuine planetary detection. As of now, no confirmed planet has been detected around either Alpha Centauri A or B, though both stars have been extensively searched. This doesn't mean no planets exist there. Detection limits for planets in binary systems are complicated by the gravitational interference of the companion star, but it does mean that the system has not yet yielded the dramatic discoveries some had hoped for. None of this diminishes the importance of Alpha Centauri as a target. The system is still the closest star system to Earth. If planetary exploration of any neighboring system ever becomes possible within a human civilization's aspirations, Alpha Centauri is the first address on the list. The question is whether we will ever develop the capability to actually get there, not just with a gram-scale probe that can't slow down, but with something capable of meaningful science, or eventually with people. That question takes us into the realm of theoretical engineering, and it is here that the terrifying nature of the distance asserts itself with full force, because when you seriously try to design a spacecraft capable of sending human beings to Alpha Centauri and returning them safely, the numbers that come out the other end of the calculation are not numbers of engineering. They are numbers of civilizational transformation. A crewed interstellar mission to Alpha Centauri faces three categories of challenge that are each independently near insurmountable with any technology conceivable in the near future, and which together compose a problem so formidable that it borders on the philosophical. The first challenge is energy, the amount of energy required to accelerate a spacecraft capable of sustaining human life to a meaningful fraction of the speed of light. Decelerate it upon arrival, and then repeat the process for the return journey is staggering. Let's work through a specific scenario. Suppose we want to send a small crew, say 6 people, to the Alpha Centauri system in a spacecraft that has enough mass to support them through a journey of perhaps 40 to 100 years. A minimal such spacecraft, even with the most optimistic mass estimates for life support, radiation shielding, food production, medical equipment, propulsion systems, and fuel, would likely weigh on the order of tens of thousands of tons. To accelerate such a spacecraft to 10% of the speed of light, which would make the one-way journey to Alpha Centauri take about 42 years, and then decelerate it upon arrival using the most efficient theoretical propulsion system currently considered plausible, nuclear fusion, rocket, would require an amount of energy equivalent to hundreds of times the current annual energy output of all human civilization, not the energy output of one nation or one century. Hundreds of times the energy output of every power plant, every combustion engine, every fire and furnace and solar panel and nuclear reactor on Earth operating for an entire year combined. This is not a technology problem. It is a civilization-scale resource problem. The kind of infrastructure required to generate, store, and deploy that much energy for a single mission implies a level of technological and economic development that is orders of magnitude beyond where humanity currently stands. Even under the most optimistic projections for the development of fusion energy, renewable infrastructure, and space-based solar power, the energy budget for a crewed interstellar mission exceeds what any civilization on Earth could plausibly mobilize for centuries. The second challenge is time. Even at 10% of the speed of light, a one-way journey to Alpha Centauri takes 42 years. For context, 42 years is roughly the time between the first moon landing and the retirement of the space shuttle. It encompasses the entirety of a professional career. An astronaut who departed at age 30 would arrive at age 72. They would live their entire adult life aboard the spacecraft, aging through middle age and into old age before reaching the destination. The people who built the ship would be dead or elderly by the time it arrived. If you want to send the crew there and bring them back, the mission duration is at minimum 84 to 100 years, more than a human lifetime for almost anyone alive today. This means that, in any realistic scenario, the crew that departs is not the crew that returns. Multiple generations would be born, live, and die aboard the spacecraft. This is the concept of a generation ship, and the social, psychological, ethical, and biological challenges of a multi-generational space voyage are in many ways even harder to solve than the engineering challenges. What kind of society forms in an enclosed metal cylinder over the course of multiple generations? How do you maintain the technical knowledge, the operational discipline, and the cultural continuity needed to operate a complex spacecraft over a century without degradation? How do you prevent the social dynamics of isolation, hierarchy, and resource scarcity from destroying the mission decades before arrival? These are not questions that engineers can answer with better materials. They are questions about human nature, and human nature has a historical track record in isolated, hierarchical, resource-constrained environments that is not particularly encouraging. There is a reason that generation ships, despite being a staple of science fiction since the early 20th century, have never been seriously proposed as near-term engineering projects by mainstream space agencies. The concept is not just technically demanding, it is sociologically demanding in ways that we do not yet know how to satisfy. The third challenge is radiation. Deep space is not empty. It is permeated by galactic cosmic rays, highly energetic particles, mostly protons and atomic nuclei, that travel through the galaxy at close to the speed of light. In Earth's magnetic field and beneath Earth's atmosphere, we are largely protected from these particles. On the International Space Station in low Earth orbit, astronauts receive radiation doses several times higher than on Earth's surface, but still within acceptable limits for missions of 6 months to a year. Beyond Earth's magnetic field, in deep space, the radiation environment is far more hostile. On a journey to Alpha Centauri lasting 40 years or more, an unshielded crew would receive radiation doses many times the threshold for acute radiation syndrome. They would develop cataracts, suffer cognitive impairment from damage to the central nervous system, face dramatically elevated risks of cancer, and potentially encounter radiation-induced damage to the reproductive system that would compromise the viability of any generation ship concept. Adequate shielding against galactic cosmic rays requires either several meters of water, polyethylene, or other hydrogen-rich material, mass that dramatically inflates the spacecraft's weight and therefore its energy requirements, or active magnetic shielding of a kind that does not yet exist in practical form. The interaction between the radiation challenge and the energy challenge creates a vicious cycle. Better shielding means more mass, and more mass means more energy, and more energy means a larger and heavier propulsion system, which means more mass, which requires more shielding. Every solution feeds back into the problem. This is the nature of interstellar engineering, a web of interdependencies that resists isolated solutions and demands a holistic technological revolution. There is, of course, another possible route, one that sidesteps some of these problems by simply not sending humans at all, at least not in biological form. The idea of sending artificial intelligence or the digitally encoded consciousness of a human being in place of biological passengers has been explored seriously by scientists like Stephen Baxter, Anders Sandberg, and others working at the intersection of computer science, neuroscience, and space exploration. If human consciousness could be faithfully digitized, a massive and deeply uncertain if, and transmitted at or near the speed of light, or uploaded onto a sufficiently powerful computer aboard a relativistic probe, then the biological challenges of interstellar travel simply vanish. A digital mind doesn't age, doesn't need food or water or oxygen, isn't harmed by radiation in the way biological tissue is, and doesn't suffer from the social dynamics of confinement and isolation in the same way a biological community would. The journey that would kill a biological crew might be entirely trivial for a digital one, but this route has its own staggering requirements. The fidelity with which human consciousness can be simulated, if it can be simulated at all, it is an open question in neuroscience that touches on some of the deepest unsolved problems in all of science. The human brain contains approximately 86 billion neurons, connected by trillions of synaptic connections, operating through a combination of electrochemical dynamics that we are only beginning to map at even the crudest resolution. Whether consciousness, subjective experience, the felt sense of being a person in a world, is an emergent property of this computational structure that could in principle be faithfully reproduced in different substrate or whether it requires the specific physical instantiation of biological tissue to exist, is a question that remains genuinely unresolved. The philosophical dimensions of this question are profound and contentious. If you digitize a human mind and send it to Alpha Centauri, and a copy of that mind remains on Earth, which one is the person? If neither is, or if both are, what does that mean for the mission, for the ethics of consent, for the whole concept of human exploration? These are not questions that can be dismissed as fanciful speculation. They are questions that any serious proposal for interstellar travel by digitized minds must grapple with honestly, and they do not have satisfying answers yet. Let's set aside these speculative futures for a moment and return to the concrete present, to what the distance to Alpha Centauri means for space science as it is actually practiced today, and what we have actually learned about the system through the instruments we have now. The most revealing thing about our current relationship with Alpha Centauri is the way we study it. We study it from here, from this solar system, with telescopes and spectrographs and interferometers that gather the light that left the Alpha Centauri system more than 4 years ago. Every photon we collect from that system carries information about a state of affairs that ended over 4 years before it arrived at our detectors. We are, in the most literal sense possible, looking at the past, not the distant past of cosmological observation, where we look at galaxies billions of light years away and see them as they were billions of years ago, but still the past. 4+ years of lag between event and observation, 4+ years of blind spot. This light speed delay is easy to intellectualize and surprisingly hard to truly internalize. When astronomers study the Alpha Centauri system, they are doing the equivalent of examining a crime scene where the evidence arrived 4 years after the crime occurred and nothing can be sent back to verify or investigate. Any event that happened in the Alpha Centauri system in the last 4 years, a stellar flare, a planetary collision, the emergence of a new signal, has not yet reached us. It is in transit, approaching at the speed of light, and we won't know about it until it arrives. The tools we use to study Alpha Centauri are genuinely impressive. The European Southern Observatory's Very Large Telescope, the Hubble Space Telescope, and now the James Webb Space Telescope have contributed detailed observations of the system's stars. The espresso spectrograph at the VLT is currently one of the most precise radial velocity instruments in existence, capable of detecting stellar velocity variations smaller than 30 centimeters per second, slow enough in principle to detect the gravitational signature of Earth-mass planets in the habitable zones of nearby stars. The next generation of ground-based telescope, the extremely large telescope currently under construction in the Atacama Desert of Chile, will have a primary mirror 39 meters in diameter, larger than any telescope ever built. Among its scientific capabilities will be the direct imaging of nearby exoplanets in reflected starlight, which for the first time might give us actual photographs, pixel by pixel images of planets orbiting Alpha Centauri, A or B, if any exist. The prospect of seeing the actual reflected light from a world that might orbit our nearest stellar neighbor, gathered by a mirror on this planet, it is extraordinary. That light will have traveled 4.24 light years to reach us, and whatever it contains, whether there is a planet, whether that planet has an atmosphere, whether that atmosphere carries spectral signatures of water vapor, or oxygen, or methane, we will be able to read it, to decode it, without leaving home. This remote sensing capability is, in a fundamental sense, the only interstellar capability we actually possess right now. We cannot go to Alpha Centauri. We cannot send probes there in any near-term time frame, but we can observe. We can gather light that has traveled 4 light years and wring information from it with instruments of extraordinary precision. In the decades ahead, our ability to do this will improve dramatically with space-based interferometers, with new generations of spectrographs, with coronagraphs capable of blocking the blinding light of a star to reveal planets thousands of times dimmer orbiting beside it. It is a strange kind of exploration by observation rather than by travel. We are like a civilization that can study a distant continent in extraordinary detail with telescopes but lacks boats. We can see the mountains and the rivers and the changing of the seasons, but we cannot feel the soil or breathe the air or hear the sounds. Whether that kind of knowledge is sufficient, whether it is a stepping stone to physical exploration or a permanent substitute for it, is one of the most important questions in the future of space science. The detection of biosignatures, chemical signatures, in a planet's atmosphere that could indicate the presence of life represents the most dramatic possible outcome of this remote sensing approach. If the James Webb Space Telescope or the next generation of instruments were to detect anomalous oxygen concentrations or methane in combination with other gases that could not persist in chemical equilibrium without biological replenishment in the atmosphere of a planet orbiting Alpha Centauri, A or B, the implications would be civilization shaking. It would be the discovery of the century, arguably of all of human history. It would be definitive or near definitive evidence that life exists beyond Earth, and yet, even then, we could not go there. The knowledge would be staggering and transforming, and the closest we could come to acting on it would be to accelerate the development of faster probes. The terrifying distance would remain exactly what it is, unchanged by our discovery, unmoved by our excitement, impervious to our ambition. This is perhaps the most philosophically disturbing aspect of the situation. Even in the best conceivable near-term scenario, we confirm life on a planet orbiting the nearest star. The distance still wins. We know it is there. We can wave hello across 40 trillion kilometers of space, and they, if they are there, if they are capable of noticing, would see the light of our civilization as it was 4 years ago, and they could wave back, and 8 years would pass before we saw their response. A conversation taking 8 years per exchange, an entire human lifespan for a few dozen sentences. The universe does not appear to have been built with conversation in mind, but let's go deeper into what the distance to Alpha Centauri means for the broader context of the Milky Way, because Alpha Centauri is not just our nearest neighbor, it is our sample point, our calibration star, the one datum we have that lets us understand just how isolated we truly are. The Milky Way is a barred spiral galaxy containing somewhere between 100 billion and 400 billion stars, spread across a disk roughly 100,000 light-years in diameter and about 1,000 light-years thick at our location. Our solar system sits in one of the spiral arms, about 26,000 light-years from the galactic center. The nearest large galaxy to the Milky Way is the Andromeda Galaxy, at a distance of approximately 2.537 million light-years. The distance to Andromeda is almost 600 times greater than the distance to Alpha Centauri. If Alpha Centauri is, as we have established, essentially unreachable with current technology in any humanly relevant time frame, then the distance to Andromeda is not just unreachable, it is cosmically meaningless in terms of any physical journey. The whole notion of interstellar travel, already strained to breaking by the 4.24 light-year gulf to Alpha Centauri, is simply vaporized by the intergalactic distances between galaxies. Within the Milky Way itself, the picture is only marginally less daunting. If we wanted to survey the galaxy, to visit a sample of its hundreds of billions of star systems, in search of life, civilization, or simply scientific knowledge, at the speeds of our fastest existing probes, we would need hundreds of millions of years. At the speeds achievable by the most optimistic theoretical propulsion systems, like nuclear pulse drives at perhaps 5% of the speed of light, crossing the diameter of the galaxy would take 2 million years. Our species is barely 200,000 years old. Our civilization, in any recognizable form, is perhaps 10,000 years old. 2 million years is 11,000 times the age of all of human civilization. This is the true scale of our problem. Alpha Centauri is our nearest neighbor, and it is already beyond our grasp. The rest of the galaxy recedes into a distance so complete, so total, that it functions less like space and more like a wall. Not a physical wall that can be broken through with sufficient force, but a temporal wall, a wall of time that no spacecraft traveling below the speed of light can penetrate without consuming timescales so vast that they make the concept of a continuous civilization maintaining the mission utterly incoherent. The only physics concept that offers a theoretical route around this wall is, of course, relativity itself. Einstein's special theory of relativity, published in 1905, predicts a phenomenon called time dilation. As a moving object approaches the speed of light, time passes more slowly for that object relative to a stationary observer. An astronaut traveling at 99% of the speed of light would experience time at a rate roughly 7 times slower than an observer on Earth. At 99.9% of the speed of light, the time dilation factor is approximately 22. At 99.99%, it is 70. At 99.9999%, it exceeds 700. This means that, in principle, and this is real physics, not science fiction, a spacecraft traveling at extremely high fractions of the speed of light could cross the galaxy within a human lifetime as experienced by its crew. From the crew's subjective perspective, only a few decades might pass during a journey that, from Earth's perspective, takes tens of thousands of years. The crew could board the ship at age 25 and arrive at a destination 100,000 light-years away at their subjective age of 60, having traveled for 35 years by their own biological clock. This is genuinely remarkable, and the physics is correct, but the engineering implications are catastrophic. To travel at 99.9999% of the speed of light, the energy required to accelerate even a small spacecraft is approximately equal to the mass energy of the spacecraft itself, multiplied by the Lorentz factor, which at that velocity exceeds 700. In practical terms, accelerating a 1,000-ton spacecraft to 99.9999% of light speed requires energy equivalent to billions of atomic bombs. This is energy that no conceivable propulsion system can provide. The efficiency with which any engine can convert mass to thrust is limited by the laws of thermodynamics, and even a perfect matter-antimatter annihilation drive, which converts 100% of fuel mass to energy, the theoretical maximum, would require carrying several times the mass of the spacecraft itself in fuel for the outbound leg alone. Antimatter itself is worth discussing here because it represents the most energetically dense propellant theoretically possible. When a particle of matter meets its antiparticle equivalent, a proton meets an antiproton, an electron meets a positron, both are annihilated and their total mass is converted to energy via Einstein's famous equation E equals mc squared. The energy density of this process exceeds that of the best nuclear fission reactions by a factor of roughly 1,000 and chemical reactions by a factor of 10 billion, gram for gram. Antimatter annihilation is the most energy-dense process known to physics, but antimatter does not exist in useful quantities in nature. It must be manufactured in particle accelerators, and the process is astonishingly inefficient. The Large Hadron Collider at CERN, the most powerful particle accelerator in existence, produces roughly 10 nanograms of antimatter per year, a 10 billionth of a gram, at a cost that estimates place in the hundreds of millions of dollars per nanogram. To produce the kilogram quantities of antimatter that would be needed to power even a small interstellar probe using an antimatter drive would, at current rates of production and cost, require millions of years and more money than the entire global economy could generate over the same period. To scale antimatter production to the levels needed for a crewed interstellar mission would require an industrial infrastructure that is not merely years or decades away from current capability. It would require a fundamental transformation in humanity's relationship to energy, manufacturing, and space-based industry that would qualify as a new epoch of civilization. Not a new era of technology, a new epoch. Even so, physicists and engineers who study interstellar travel seriously continue to investigate these concepts, not because they expect to build antimatter drives next century, but because the exercise of working through the requirements clarifies the magnitude of what is needed. It establishes a baseline. It tells us, with mathematical precision, not just how hard the problem is, but exactly what class of civilization would be needed to solve it. And the answer, consistently, is a civilization far more advanced than we are today in energy production, materials science, manufacturing capability, and perhaps most importantly, in the willingness to dedicate civilizational resources to a project that will not return results within any individual's lifetime, or possibly within dozens of generations. This brings us to a concept introduced by the Soviet astronomer Nikolai Kardashev in 1964, which has since become a standard framework in discussions of advanced civilizations, the Kardashev scale. Kardashev proposed classifying civilizations by their energy consumption on a logarithmic scale. A Type 1 civilization controls all the energy available on its home planet. A Type 2 civilization controls all the energy output of its host star. A Type 3 civilization controls the energy output of its entire galaxy. Current human civilization is estimated to be approximately at a Kardashev level of 0.73, not yet Type 1. We do not even fully control the energy resources of our own planet. The energy output of our sun, roughly 3.8 times 10 to the 26th power watts, exceeds the entire energy consumption of human civilization by a factor of more than 1 billion. We are, by the Kardashev standard, an infant civilization, a Type 2 civilization, one that has fully harnessed its star's output, perhaps through a Dyson sphere or Dyson swarm of solar collectors, would command energy resources adequate to begin contemplating genuine interstellar missions. Not comfortable missions, not journeys with abundant safety margins, but missions that the physics does not absolutely forbid. The step from Type 0.73 to Type 2 is not a step. It is a transformation so profound that the civilization on the other side of it would be almost unrecognizable to us. The distance to Alpha Centauri, in this framing, is not a challenge that any civilization at our current level of development is equipped to solve. It is a challenge calibrated to the capabilities of a civilization that has mastered its own solar system, harnessed its own star, and developed manufacturing and engineering capabilities that we can only gesture toward in theoretical terms. The terrifying thing is not that the distance cannot be overcome. The terrifying thing is the gap between where we are and where we would need to be to overcome it. And yet, the distance to Alpha Centauri is also, seen from a different angle, a kind of extraordinary gift because it is close enough for us to see, close enough for us to study in detail, close enough that we can detect the subtle gravitational signatures of planets orbiting its stars, and within a decade or two, perhaps directly image those planets in reflected light, close enough that the light we receive from it is rich in information, spectral data, variability data, proper motion data, accumulated over more than a century of careful observation. Our knowledge of Alpha Centauri is, in many ways, more detailed and more precise than our knowledge of many stars within the Milky Way's spiral arms. We know the masses, radii, surface temperatures, luminosities, chemical compositions, ages, and space motions of Alpha Centauri A and B to extraordinary precision. We know the orbit of the binary system, the orbital period of Proxima around the pair, the flare statistics of Proxima's magnetic activity, the chromospheric structure of its surface. We have more detailed stellar models of this system than of virtually any other stars outside the solar system, and this knowledge matters because it is the foundation on which any future mission to the system would be built. Every data point gathered by every telescope aimed at Alpha Centauri over the last century is a brick in the foundation of an eventual interstellar mission. The day that humanity is technologically ready to send something to Alpha Centauri, a gram-scale probe in the near term, something more substantial in a more distant future, the system waiting at the destination will not be unknown. It will have been studied for centuries. We will arrive, in whatever form we arrive, with prior knowledge, with context, with a scientific framework built from 150 years of painstaking observation. This is what the scientific study of Alpha Centauri really represents. Not just curiosity for its own sake, not just the accumulation of knowledge in the abstract. It is reconnaissance for a mission that hasn't been planned yet, by a civilization that hasn't built the ships yet, in a future that may be centuries away. Every astronomer who has pointed a telescope at that system and measured its properties has contributed a small piece to a puzzle that future generations will complete in ways we cannot yet imagine. Now let's talk about the concept of the interstellar medium, the space between stars, because it is not nothing, and understanding what it actually is adds another dimension to the terrifying nature of the distance. The interstellar medium is the matter and radiation that permeates the space between star systems. It is not a perfect vacuum. It contains gas, primarily hydrogen and helium, in both neutral and ionized forms, at densities so low that they would qualify as an extraordinarily hard vacuum by any laboratory standard on Earth, but which are nonetheless present. In the local bubble, the region of the galaxy that contains our solar system, the density of the interstellar medium is especially low, perhaps 0.003 atoms per cubic centimeter, compared to the roughly 0.05 atoms per cubic centimeter that characterizes the average interstellar medium in the galaxy at large. The local bubble is a region excavated by a series of supernova explosions roughly a few million years ago, leaving behind a cavity of hot, low-density gas. Our solar system, along with Alpha Centauri, sits within this bubble. Even at these extremely low densities, a spacecraft traveling at a significant fraction of the speed of light would encounter the interstellar medium as a constant bombardment of particles. At 10% of the speed of light, each hydrogen atom the spacecraft's surface encounters carries the energy of a very fast-moving particle. Not individually dangerous, but in aggregate, over 40 years of travel, delivering a cumulative radiation dose that would require substantial shielding. At 20% of the speed of light, the breakthrough starshot target velocity, individual dust grains, even ones just a few micrometers in size, carry the impact energy of bullets. A millimeter-sized dust grain at this speed carries the kinetic energy of a medium-velocity rifle round. For a gram-scale sail, this represents a potentially catastrophic collision. The probability of encountering such a grain during a flight through the local bubble over the 4.24 light-year distance to Proxima Centauri is not zero. It is calculable. The dust density in the interstellar medium, combined with the cross-sectional area of the spacecraft and the distance traveled, gives a specific probability of impact. Breakthrough Starshot's team has estimated that for their proposed sail design, the probability of a catastrophic dust impact is low, but not negligible, and dust abrasion, the cumulative effect of micrometer-scale particles gradually eroding the sail surface, represents one of the primary engineering challenges to be solved. This is a reminder that space, even the empty space between stars, is not passive. It is a physical environment with its own hazards, its own structure, has its own demands on any vehicle that attempts to cross it. The interstellar medium is to a relativistic spacecraft what the ocean is to a ship. Not solid, not opaque, not dangerous in an immediately obvious way, but capable of destroying the vessel if the vessel is not designed to handle its properties. There is also the question of what space the spacecraft would be traversing in terms of gravitational environment. Between our solar system and Alpha Centauri, there are no significant gravitational bodies, no planets, no brown dwarfs, no rogue planets large enough to affect a spacecraft's trajectory in any major way, as far as we know. The trajectory would be dominated by the gravitational influence of the Sun at departure, the gravitational influence of Alpha Centauri at arrival, and the extremely weak gradient of the galactic gravitational field in between. This simplifies navigation in one sense and complicates it in another. Without gravitational assists, every change in velocity must come from the spacecraft's propulsion system, and the trajectory must be planned and executed with extraordinary precision years in advance. A communication link maintained over the growing distance during the journey would experience degradation, not just due to the increasing distance, and therefore decreasing signal strength, but also due to relativistic Doppler shifts that would shift transmitted frequencies and the time dilation experienced by the spacecraft relative to Earth. For a mission traveling at relativistic velocities, the communication systems would need to account for these effects at every stage, and the growing delay would make any real-time guidance from mission control impossible. The spacecraft would need to be more autonomous than any vehicle ever built by humanity, making life or death decisions without the possibility of consulting its creators. This autonomy requirement applies not just to navigation, but to every system aboard: life support, power management, propulsion, scientific instrumentation, medical systems for a crewed mission. Every possible malfunction, every conceivable emergency, every operational decision must be anticipated and addressed in the onboard software and hardware before departure, because once the spacecraft is en route, it is on its own. There are no repair crews, no spare parts deliveries, no software updates from home that can arrive in time to be useful. The spacecraft must be, in effect, a complete and self-sufficient civilization in miniature, capable of sustaining itself for decades in the most hostile environment imaginable, without any external support. This requirement for radical self-sufficiency is, in many ways, the defining engineering challenge of interstellar travel. It is what separates the deep space missions of the near future from interstellar missions philosophically as much as technically. Every mission we have ever launched, even the Voyager probes, even the New Horizons spacecraft currently passing through the outer solar system, has remained in continuous communication with Earth. We can upload new software, diagnose problems remotely, adjust mission parameters in response to new information. The relationship between the spacecraft and its controllers is constant and interactive. An interstellar mission breaks that relationship irreparably. The spacecraft that leaves for Alpha Centauri is, from the moment of departure, a separate entity, operating on its own, making its own decisions, pursuing its own mission according to instructions that cannot be updated in any meaningful sense after the first few years of travel. It is the loneliest object that humanity will ever have created. Whether that object contains human beings or artificial intelligence or some combination, it will spend decades in absolute isolation, a solitary artifact of a civilization that launched it and will never be able to fully follow the details of its journey in real time. And when it arrives, if it arrives, and begins transmitting data back to Earth, those signals will take 4.24 years to reach us. The crew or the AI will have made every discovery, solved every problem, experienced every joy and catastrophe 4.24 years before we know about it. We will hear about the first sight of Alpha Centauri b growing large in the forward sensors as a historical record, not a live broadcast. We will learn of any discoveries about the system's planets from the past, not from the present. This temporal disconnection is one of the most profound and underappreciated aspects of what interstellar exploration would actually mean for the relationship between the explorers and the civilization that sent them. The explorers would know at every moment that they were operating in a realm of experience that their home civilization could not share. Every decision they made would be made without any possibility of consultation with Earth. They would be pioneers in a way that no human being has ever been. Not Magellan, not the Apollo astronauts, not the crews of Antarctic expeditions, because all of those previous explorers could, in extremis, eventually be found or reached or communicated with. An interstellar crew cannot, not for years, not for decades. The psychological literature on extreme isolation, on long duration Antarctic wintering missions, on simulated Mars missions, on the experiences of solitary circumnavigators, is deeply instructive about the mental health challenges of prolonged isolation from familiar social structures. Researchers studying these environments have documented a phenomenon called the third quarter phenomenon, a marked increase in negative mood, interpersonal conflict, and motivational decline at approximately the 3/4 point of a long, isolated mission. The psychological effects of knowing that you are years away from any external contact, that any emergency must be handled internally, that the world you left behind is aging and changing in your absence. These are not trivial obstacles. They are fundamental aspects of the human condition that any crude interstellar mission would need to address with a seriousness and a scientific rigor equal to the engineering challenges. Some researchers have proposed that the solution to the psychology of interstellar travel lies in genetic and neuropharmacological engineering, modifying the crew at the biological level to reduce the need for social stimulation, to increase resilience to isolation, to alter the subjective experience of time. Others have proposed hibernation or suspended animation as a way of simply eliminating the subjective experience of the journey, allowing the crew to depart, sleep, and wake at their destination with little psychological burden from the intervening years. Both approaches are possible in theory and have been studied seriously, but both involve modifications to the human being, to what it means to be the person on the mission, that raise profound ethical questions. Is a person whose neurobiology has been engineered to tolerate isolation the same person who consented to the mission? Is a person who has spent 40 years in suspended animation, biologically aging only a few months, still the same person in any meaningful sense? These are not idle philosophical questions. They are questions that would need to be answered before any civilization could ethically launch a crewed interstellar mission, and the answers are not obvious. The distance to Alpha Centauri, in the end, is not just a number in a physics textbook. It is a pressure that bears down on every aspect of the problem of human expansion into the universe, on engineering, on physics, on biology, on psychology, on ethics, on the deepest questions of what our species is and what it wants to become. It compresses all of those questions into a single, concrete challenge. How do you cross 40 trillion kilometers with enough of yourself intact to make the crossing meaningful? There are scientists and engineers who believe the answer will come within a few centuries. There are others who believe the distances between stars represent a fundamental, permanent limit on the spread of biological life through the galaxy, that physics simply will not cooperate with the ambition of flesh and bone, and that the stars will remain unreachable for creatures like us, no matter how clever we become. There are philosophers who believe the question of interstellar travel is not really about engineering at all, but about the nature of consciousness and the possibility of forms of life and mind so different from our current selves that the comparison is meaningless, that the civilization which eventually crosses the gap to Alpha Centauri will have so little in common with the one that dreamed of doing so that the word humanity will need to be redefined. All of these positions are held by thoughtful people. None of them can currently be proven or disproven. The distance itself simply sits there, 4.24 light years, 40 trillion kilometers, 268,770 astronomical units, as patient and indifferent as the universe itself, waiting for something to cross it. When I say the distance to Alpha Centauri is terrifying, I mean this in a very specific sense. Not terrifying the way a horror film is terrifying, not threatening or menacing in a way that demands an emotional response of fear. Terrifying in the sense of awe, the old meaning of the word, the sense of something so immense and so beyond the scale of ordinary experience that the mind recoils not from threat, but from sheer incomprehension. There is a word for this in the philosophical literature, the sublime. Edmund Burke and Immanuel Kant both wrote about the experience of encountering something so vast that it exceeds the capacity of imagination to contain it. The ocean seen from a cliff, a mountain range, the night sky itself. The experience of the sublime involves a kind of pleasurable terror, a recognition of the smallness of the self in the presence of something incomprehensibly large, followed by a compensating feeling of the mind's ability to conceive of and in some sense encompass what the body could never physically match. The distance to Alpha Centauri is sublime in exactly this sense. It is too large to genuinely comprehend. Every analogy and comparison we reach for fails eventually. Every model that brings it down to human scale distorts something essential about what it actually is. And yet, the mind keeps reaching, but keeps trying, because that reaching, that insistence on grappling with the incomprehensible, is one of the most distinctively human things there is. We did not look up at the night sky and see Alpha Centauri for millions of years without knowing what it was. It was just a bright star in the southern sky, a navigation point for ancient peoples of the southern hemisphere, a fixed landmark in a world of uncertainty. The indigenous peoples of Australia knew it well. The ancient Egyptians observed it, as did the Polynesians, who used the stars to navigate across the Pacific. For most of human history, it was simply light, a point of beauty in the dark. Then we began to understand what it was. Edouard Servet, Ernest Przybylski, Nicolas, Louis de Lacaille, and others mapped it in the 18th century. Thomas Henderson, a Scottish astronomer working at the Cape of Good Hope, first measured its parallax in the 1830s, establishing its distance with the first real measurement of a stellar distance ever made. The method he used, observing the tiny apparent shift in the star's position against the background of more distant stars as the Earth moved from one side of its orbit to the other was so elegant in its simplicity and so extraordinary in what it revealed. He pointed his instruments at this bright southern star, measured its position with painstaking care over months of observation, and from those measurements pulled out, for the first time in history, a number that told us how far away the stars actually are. The number was, even to Henderson himself, almost inconceivably large. He delayed publishing his results for years, partly because of other commitments, and partly, one suspects, because a result that says the nearest star is more than 25 trillion miles away in an era when the measurement of any distance beyond the solar system was entirely new, was not the kind of number you rushed to announce. It was the kind of number you checked, and checked again. But he was right, and the number has held up through 180 years of increasingly precise measurement, through the work of Hipparcos and Gaia space astrometry missions, through modern interferometry and spectroscopy, through every technique we have ever devised for measuring cosmic distances. Alpha Centauri A and B sit 4.37 light-years away. Proxima Centauri, at 4.24 light-years, is marginally closer. These numbers are known to extraordinary precision, not approximately, not as rough estimates, but as genuine, rigorously measured values that carry uncertainty in only the final decimal places. In knowing these numbers with such precision, we have done something remarkable. We have mapped the distance to another star with an accuracy that Henderson in 1839 could not have imagined. We have extended the reach of human measurement from the scale of our solar system to the scale of the interstellar medium, a leap of roughly 100,000 times in the range of what our instruments can precisely probe. It is one of the great achievements of observational science, and it has given us a gift that is hard to fully appreciate. We know with certainty how far away the nearest stars are. The fact that that certainty is also a kind of sentence, a measured, confirmed, yet undeniable articulation of our isolation, is the paradox at the heart of what it means to study the cosmos. The better we understand the universe, the more clearly we see the walls of the room we are in. Every advance in observational astronomy has extended our knowledge of what is out there, while also confirming the distances that separate us from it. The Milky Way is not a comfortable home. It is an address in a universe where the neighbors are light years away and the roads between us are measured in technologies we do not yet have. But consider also the other side of that coin. Consider what it means that a species of primate evolved on a rocky world around an unremarkable star in the outer suburbs of an ordinary galaxy, managed not only to survive long enough to develop science and technology, but to accurately measure the distance to the nearest stars with instruments made of glass and metal and mathematics. We have never been to Alpha Centauri. We have never sent anything near it. We have looked at it from here with human-made devices, and we have calculated its distance to a precision of a fraction of a percent. That is extraordinary. The same species that cannot travel to Alpha Centauri has nonetheless mapped it, has characterized its stars, searched its system for planets, begun to understand the potential habitability of worlds we cannot yet visit. The aspiration is intact, even if the capability is not yet there. The dream is older than the science, and the science is catching up to the dream, even if the engineering has a long way to go. When the day eventually comes, and whether it comes in 100 years or 1,000, whether it involves a gram-scale probe or something more, whether it is crewed by biological humans or artificial minds, or something in between that we cannot yet name, when that day comes and something built on Earth crosses the gap and enters the Alpha Centauri system for the first time, it will be one of the defining moments in the history of this planet, not just in the history of human civilization, in the history of Earth as a biosphere. It will be the moment when life, carbon-based, oxygen-breathing, 4 billion-year evolved life from this particular rock, reaches out and touches another star system. The moment when whatever tenuous thread connects us to the rest of the galaxy is first pulled taut by something more than light. We are not at that moment yet. We are so far from it, measured by current technology, that it would be dishonest to suggest it is close. But the fact that we can talk about it with real physics, with real numbers, with an understanding of what it would actually require that is grounded in known laws of nature rather than speculation. That itself is progress. A few centuries ago, the nature of the stars was unknown. A few decades ago, the existence of planets around other stars was unconfirmed. Now we know the distances, the stellar compositions, the orbital architectures of thousands of planetary systems, and the theoretical physics of the propulsion systems that could, eventually, bridge the gap. The distance to Alpha Centauri is terrifying. It is 40 trillion kilometers of hard vacuum and radiation and absolute silence, guarded by physics that tolerates no shortcuts and punishes ambition with merciless arithmetic. It is a chasm that makes every achievement of human engineering look like a child's first steps. It is a number that, when truly unpacked, tells us something uncomfortable and unavoidable about our place in the universe, that we are small, that we are slow, that the cosmos was not built to accommodate our curiosity or our dreams, but it is also the nearest star, the very closest one, and it is right there, 4.24 light years away, burning quietly in the southern sky, orbited perhaps by worlds, perhaps by something more. It has been there for billions of years, and it will be there for billions more, patient in the way that only astronomical objects can be patient, indifferent to whether we ever arrive, indifferent to whether we ever even try. We are, for now, the species that looks up, that measures, that calculates and plans and dreams across distances that the universe has made ridiculous to dream across. The distance to Alpha Centauri is the measure of how far we have yet to go. It is also, somehow, the measure of how far we have already come, from fire and stone and naked eyes scanning the sky, to particle accelerators and space telescopes and interstellar mission concepts backed by real physics and real funding. The stars are terrifyingly far away. They always have been, and we keep looking at them anyway. That may be the most human thing of all, but let's not end there, because there is one more dimension to the story of Alpha Centauri that demands to be told, a dimension that pulls the entire discussion from the abstract into the viscerally personal. And that dimension is the story of what it would actually feel like to make the journey, if you could make it. Not the engineering, not the physics expressed as equations, the experience as a human being of traveling to another star. Close your eyes for a moment and try to inhabit the departure. You are aboard a spacecraft, let's say the most optimistic crewed interstellar vessel that serious scientists have imagined. Nuclear pulse, driven, massive, shielded, carrying a crew of 12 people. You have spent years training for this mission. You have said goodbye to everyone you know. You have watched the Earth recede in the aft cameras, first to the size of a marble, then to a bright blue star, then to an unremarkable point of light, indistinguishable to the naked eye from Venus on a clear night, and then nothing, just the sun, still blinding and enormous and warm, filling space with its light and its wind. In the first weeks, the sun is your anchor. It dominates the sky the way it dominates the inner solar system. Familiar, present, reassuring. You are still, in a meaningful sense, within the sun's domain. The solar wind still touches your spacecraft. The sun's gravity still bends your trajectory. You are an extension of the solar system, a piece of it that has broken loose but not yet broken free. Then the sun begins to shrink, not gradually, so you barely notice, but measurably. Week by week, the solar wind thins and then fades to nothing as you cross the heliopause, the invisible boundary where the sun's influence yields to the interstellar medium. On the other side of that boundary, you are truly in interstellar space for the first time. The sun behind you has become a star, still the brightest star in your sky, but unmistakably a star rather than a sun. Its light still reaches you, still illuminates your solar panels, still provides energy, but it no longer warms you in the way a sun warms a world. It is a lamp seen from a great distance, not a fire you are standing near. Ahead of you, Alpha Centauri. Even at the start of your journey, it is already brighter than it appears from Earth, not by a large margin, but enough to notice. As the years pass and you creep closer at your fraction of the speed of light, its brightness will increase. The two stars of the main binary, A and B, will gradually resolve into two distinct points of light, a feat impossible to the naked eye from Earth. They will begin to look like two suns, 2 destinations. The system you have been traveling toward for years will finally begin to look like a place rather than just a direction. But those years in between, the 40 or 50 or 80 years of the journey, depending on the velocity your craft can achieve, those years are the story that science fiction has always wrestled with and never fully solved, because space does not change. This is the fundamental psychological fact that distinguishes interstellar travel from any other kind of exploration in human history. On a ship crossing an ocean, the environment changes. Weather patterns shift, currents alter, wildlife appears, the color of the water changes. On a voyage through the interstellar medium, nothing changes. The stars move imperceptibly slowly across the sky over the course of months, not because they are moving, but because your own trajectory is shifting their apparent positions minutely over time. The background of more distant stars, the faint wash of the Milky Way, the occasional bright nebula, these things are constant, unchanging, as static as a painted backdrop. The experience of time in this environment would be unlike anything humans have ever endured, not the relatively manageable isolation of an Antarctic winter over station, where the sun sets and rises and the seasons still assert their rhythm, where resupply flights can theoretically come, where radio contact with the outside world is continuous, not the 6-month increments of the International Space Station, where the Earth turns beneath you and the Terminator line sweeps across continents every 90 minutes, and you can look down and see weather and cities and the blue skin of the world you came from. In interstellar space, there is none of that. There is the ship, there are your crewmates, there are the instruments and the systems and the work, always the work of maintaining and monitoring and recording. And there are the stars, which are beautiful and eternal and absolutely, utterly static. The human brain was not built for this. It was built for environments that change, environments that provide feedback, that reward action, that create a sense of progress and consequence. The entire architecture of human motivation is based on the experience of cause and effect on timescales from seconds to years. When you work in a garden, the seeds you plant become sprouts, become fruit within months. When you build something, the structure rises day by day. When you travel across terrain, the landscape shifts and the destination draws nearer in ways the eye can perceive. All of this feedback is the engine of human psychological function, and interstellar travel eliminates it almost entirely. The destination gets closer by 0.1 light years per year if you are traveling at 10% of the speed of light, but there is no way to see that change from aboard the spacecraft. The apparent brightness of Alpha Centauri increases infinitesimally slowly, a change measurable only by instruments over periods of months. The sense of motion, of progress, of actually getting somewhere is almost completely absent from any moment-to-moment experience of the journey. You know, intellectually, that you are the fastest moving human beings in history. You know, from the instruments, that the distance is decreasing, but you do not feel it, not in your body, not in your senses, not in any of the channels through which the human nervous system usually understands the world. The crew members who would be best suited to such a journey, who would maintain their psychological equilibrium and their operational effectiveness over decades in this environment, would likely be individuals with temperamental profiles quite unlike the extroverted, high sensation-seeking personalities that popular culture often associates with astronauts. The best interstellar crew members might be people of extraordinary inner resources, contemplatives, scholars, people who find deep satisfaction in slow, patient, more careful work rather than action and immediate feedback. Monastics, in a sense, people capable of living fully and richly within the confines of a vessel and a mission and a community, without the need for external variety or stimulation. The crew would also develop, over the decades, a culture entirely their own, shared references, private language, rituals and customs that developed organically in the particular closed environment of the ship. They would become, in a sense, a society, small but complete. Their children, if the mission was multi-generational, would know only this world. The vast majority of their life experience would be the ship, the crew, the routine of maintenance and science, the slow and unchanging starfield outside the windows. Earth, for them, would be something closer to mythology than memory. What would it mean to know, as a person born on an interstellar vessel, that you were destined to spend your entire life aboard it, that you had not chosen this mission but been born into it? The ethics of generation ships are genuinely fraught in ways that most enthusiasts of the concept prefer not to dwell on. The people who launch the ship consent to the mission. The people born en route do not. They inherit a life they did not choose, bounded by walls they did not build, dedicated to a destination they will likely not live to see. Their children's children might be the ones who arrive at Alpha Centauri, and what relationship would those great-grandchildren of the original crew have to the mission, to the Earth that launched it, to the civilization that built the ship? Would they feel obligation or resentment, or simply neutrality about the world they were born into? These are not questions with clean answers. They are questions that have occupied legal scholars, bioethicists, and science fiction writers in roughly equal measure. And the consensus, to the extent one exists, is that there is no consensus. Generation ships involve a profound act of coercion over the unborn, a fact that does not automatically disqualify them ethically, since the same coercion exists in every society that chooses what language to teach its children and what culture to immerse them in, but which is orders of magnitude more severe in the case of an interstellar voyage where the children literally have nowhere else to go. The alternative, that everyone aboard the ship should live to see the destination, requires either very fast travel, which demands extreme energy and engineering, or suspended animation, which demands medical technology we do not yet possess. Cryogenic suspension, the freezing of biological tissue at very low temperatures, is possible for individual cells and simple organisms, but has never been achieved for complex multicellular organisms without causing irreversible cellular damage from ice crystal formation. Research into vitrification, replacing cellular water with glass-forming substances that prevent ice crystal formation, has produced encouraging results in laboratory settings, but the application to whole mammals, let alone whole humans, remains unachieved. If it were achieved, the ethical landscape of interstellar travel would shift substantially. A crew placed in suspended animation would not experience the journey subjectively. The 40 or 80 years of travel time would pass as what might feel, upon awakening, like a long and dreamless sleep. The psychological burden of the journey would be enormously reduced. The biological aging that would otherwise render the crew elderly or dead by arrival would be halted. The ship could be largely automated for the transit phase, requiring only minimal active maintenance. And the crew that arrived at Alpha Centauri would be, biologically and psychologically, the same crew that departed Earth, with memories intact, skills intact, relationships intact. The challenge, of course, is that, if it were achieved, is doing enormous work in that scenario. Suspended animation for humans currently falls somewhere in the gap between not impossible in principle and nowhere near achievable with current biology or medicine. The mechanisms of cellular damage during freezing and thawing are well understood at the molecular level, but the solutions remain elusive. This is a problem where progress is measurable in decades, not years, and where the jump from suspended laboratory tissue to suspended living human will require a breakthrough in our understanding of complex biological system resilience that may or may not be forthcoming. Still, it represents one of the most directly practically important areas of research for the future of interstellar exploration, and it attracts serious scientific attention in ways that go beyond the space travel application. Suspended animation has obvious medical applications for trauma care, for organ preservation, for cancer treatment that have driven significant investment, independent of any interstellar mission concept. Now let's turn back to the sky, because there is one more thing to consider about Alpha Centauri that puts the entire discussion in a different register, and that is its future. Not our future in relation to it, but the actual physical future of the Alpha Centauri system and of its relationship to ours. Stars are not stationary. They orbit the galactic center, each following its own trajectory through the Milky Way's gravitational field, and these trajectories mean that the stars we see around us today are not the same stars that were our neighbors millions of years ago, and will not be the same stars that are our neighbors millions of years hence. Alpha Centauri is currently moving through space relative to our solar system at a velocity of roughly 22 kilometers per second. This relative motion is bringing it very slowly closer to us over the coming millennia. In approximately 27,000 years, Alpha Centauri will reach its closest approach to our solar system, coming within about 3 light-years of the Sun, somewhat closer than its current 4.24 light-years. After that, it will gradually recede, and in a few 100,000 years, it will have moved to a distance where it no longer holds the title of nearest stellar neighbor. Another star, currently further away, will have drifted into that position. This cosmic game of stellar neighbors, the slow shuffling of star systems past each other over millions of years as they orbit the galactic center, is a reminder that the universe is not static on any timescale. The configuration of stars we see tonight is a snapshot of a continuously evolving arrangement. The stars that were our nearest neighbors when our solar system was young, 4.5 billion years ago, were entirely different from the ones that surround us now, and the stars that will be our nearest neighbors in 1 billion years will be different again. In this context, Alpha Centauri's position as our nearest neighbor is a temporary fact, temporary on cosmic timescales, but deeply significant on the timescales of human civilization. For the next tens of thousands of years, it will remain the closest star system to Earth, the benchmark against which all our aspirations for interstellar travel are measured. If we are ever going to become an interstellar civilization, the first step will almost certainly be in the direction of that faint yellow and orange glow in the southern sky. There is something almost poignant about that temporal specificity. Humanity has existed as a complex, technologically capable civilization for perhaps 10,000 years. We have the potential, under optimistic scenarios, to remain a technological civilization for millions of years or more, to develop the kind of capabilities needed for genuine interstellar travel somewhere in the vast spread of time ahead. And the star that will mark the first interstellar destination, the one that will be closest when we finally develop the capability to make the crossing, is Alpha Centauri, a star that happens to be nearby right now, in this brief cosmic moment when we are first becoming aware of what it would mean to reach it. Whether that is coincidence or something more meaningful is a question that science cannot answer. The universe does not arrange itself to suit our dramatic sensibilities, but it is a remarkable alignment of circumstances nonetheless, that the species that first developed the scientific tools to understand stellar distances, and that is now beginning to develop the engineering tools to contemplate crossing them, happens to live in an era when the nearest star is 4.24 light-years away, rather than, say, 40 light-years or 0.4 light-years. The distance is large enough to be a genuine and formidable challenge, but small enough to remain conceivably within reach of a sufficiently advanced version of our civilization. It is, in the most literal sense, the most approachable problem of interstellar science, and the approaches being taken to it, the serious scientific programs, the private initiatives, the theoretical work, represent a genuinely new chapter in the history of human exploration. For most of human history, exploration meant going somewhere you could physically travel to. It meant boats and horses and feet on the ground. Then it meant aircraft and spacecraft. The notion of interstellar exploration is only a few decades old as a serious scientific field, rather than a literary conceit. And already it has attracted the attention and resources of some of the most accomplished scientists and engineers alive. The Breakthrough Starshot Initiative, which we discussed earlier, is the most funded and most technically detailed current proposal. But it is not the only serious idea. There are researchers studying electromagnetic launch systems, essentially enormous railguns in space that could accelerate small probes to significant fractions of the speed of light without requiring the probe to carry its own propellant. There are proposals for using solar sails driven by the sun's own radiation pressure, building speed gradually over years of continuous acceleration through the inner solar system before being aimed outward at a target star. There are theoretical studies of ramjets that could scoop interstellar hydrogen as they travel, using it as both fuel and propellant in a fusion drive, though the physics of the Bussard ramjet, as this concept is known, turn out to be far more demanding than its elegant theoretical premise suggests. there are also longer-term concepts that begin to stretch the boundaries of what current physics would consider achievable, but that are not, in principle, forbidden by known laws of nature. Alcubierre drive concepts, theoretical space-time geometries that could allow a spacecraft to move faster than light by contracting space in front of it and expanding space behind it, without the craft itself exceeding light speed relative to its immediate space-time neighborhood, remain objects of serious, if highly speculative, theoretical investigation. The energy requirements for an Alcubierre drive, as originally formulated, were absurdly enormous, more than the mass energy of Jupiter, concentrated in a particular geometric configuration. Subsequent refinements have reduced the theoretical energy requirements substantially, though they remain far beyond anything achievable. And whether the space-time geometry required is physically stable, and whether it could be created in practice, remains deeply uncertain. Wormholes, solutions to Einstein's field equations that connect distant regions of space-time through a shortcut, are another concept that exists at the boundary between serious theoretical physics and speculation. The mathematics of wormholes is well developed. They are genuine solutions to general relativity, but their physical existence requires exotic matter with negative energy density, a form of matter that has not been observed to exist, though quantum field theory allows for states with locally negative energy density in specific circumstances. Whether macroscopic, traversable wormholes can exist in nature or could be artificially constructed by sufficiently advanced technology is a question that remains genuinely open, though most physicists consider it vanishingly unlikely in the context of any near or medium-term future. These exotic concepts deserve mention, not because they are engineering proposals, but because they illustrate the frontier of human thinking about the interstellar problem. When smart people sit down and ask seriously how any civilization might eventually cross the distances between stars, the answers they come up with range from the brutally practical, bigger lasers, smaller probes, to the speculative, manipulated space-time, exotic matter, and the entire range is united by the recognition that the problem is real, that physics takes it seriously, and that the distance will not yield to anything less than creative and rigorous engagement with fundamental science. The history of science contains many examples of problems that seemed insurmountable to one era and were solved in the next, not by brute force, but by a conceptual revolution that reframed the problem in a way that made solutions visible that were previously invisible. Powered flight seemed impossible until the Wright brothers flew in 1903, not because the physics were unknown, but because the engineering approach had been wrong. Nuclear energy seemed like an abstract theoretical curiosity until it wasn't. The structure of DNA seemed impenetrable until Rosalind Franklin's X-ray crystallography gave Watson and Crick the key image that unlocked the double helix. In each of these cases, the breakthrough came not from scaling up known approaches, but from finding a fundamentally different way of thinking about the problem. Whether interstellar travel will yield to such a breakthrough, whether there is a conceptual revolution waiting somewhere in the future, physics that will transform the problem the way the Wright Flyer transformed powered flight, is unknowable from where we stand. It may be that the laws of physics, as we understand them, and as they will be understood by any future physics, simply do not permit any route across the interstellar distances that is fast and cheap enough to be practically useful for biological beings on civilizational timescales. It may be that the stars are genuinely, permanently beyond our reach in any meaningful physical sense. Or it may be that somewhere in the vast unexplored terrain of physics beyond the standard model, beyond the current formulation of general relativity and quantum mechanics that we know must eventually be superseded by a deeper theory, there is a principle or a phenomenon that changes the equation, something we do not yet know, that future generations will understand in the way we understand electromagnetism or nuclear forces, as a natural phenomenon with practical applications that flow from its correct understanding. We cannot know, and that uncertainty, that genuine, scientific, non-dismissible uncertainty about what future physics will look like, is part of why the dream of interstellar travel persists even in the face of calculations that seem to foreclose it. The distance is terrifying, and the physics as currently known is formidably hostile. But physics has surprised us before. It may surprise us again. In the meantime, while the engineers dream and the physicists calculate and the philosophers debate, the light keeps arriving. Every night that is clear and dark enough, photons that left the Alpha Centauri system 4.24 years ago complete their journey and land on the retinas of anyone who looks up at the right patch of sky in the right part of the world. 4 years of travel, 120 million kilometers per day, and at the end of it, a human eye lies on the surface of a small rocky world, receiving the message: we are here, we are shining, we are 4.24 light years away. Come, if you can, or look, if you cannot, we will be here. The stars do not say this, of course. They do not say anything. They simply burn, indifferent to whether anyone receives their light, indifferent to whether anything in the universe is watching. The meaning in that light is entirely the one we bring to it, the curiosity, the aspiration, the longing that is so characteristically human. The universe provides the photons, we provide the wonder. The distance to Alpha Centauri is 4.24 light years, or 40 trillion kilometers, or 268,770 astronomical units, or 25 trillion miles, or 73,000 years at Voyager. 1 speeds. It is the smallest interstellar distance our solar system offers. It is still effectively infinite by the standards of every technology we currently possess. It is not a problem we have solved, or are close to solving, or will solve within any foreseeable near term. It is a wall at the edge of our solar system, made not of stone or metal, but of physics and time, and it has not moved and will not move no matter how hard we push against it. But we are still pushing. We are measuring it with extraordinary precision. Studying the system it separates us from with the best instruments ever built, theorizing about how it might eventually be crossed, and building the first, tentative, gram-scale steps towards sending something across it. We are, as a civilization, approximately 5 seconds into a marathon that will take centuries or millennia to complete. And that is not a discouraging thing if you understand what it means. It means the race has started. The enormity of what remains to be covered is matched and perhaps exceeded by the audacity of having begun at all. The stars are terrifyingly far away. We are looking at them anyway. We are measuring them anyway. We are dreaming across the abyss anyway. That has always been how it starts.